Unit 11A will be our introduction to waves. A wave is a disturbance in a medium that travels outward from a source point. Some examples of waves could be like the surface of water that is disturbed in a water wave, or the Earth's crust that experiences a disturbance in an earthquake wave, or a sound wave which experiences a disturbance in the air pressure through which the sound is traveling. Here is an example of a simple wave that's being created by a string under tension. If we send a wave through that string, it will transmit all the way throughout that medium and travel with a peak or a crest and a trough or a valley. Just like we had with oscillations, these waves have similar oscillation-like quantities. There are two major kinds of waves that we can have. We can have a wave pulse, which is a singular disturbance that is sent through a medium, or we can have a continuous wave that has repetitive disturbances being sent through a medium. So here's an example of a wave pulse versus a continuous wave or a periodic wave. The wave pulse just exists as one bump in this string, whereas the periodic wave has many wave pulses within it. We're going to look at water waves, or the string under tension, as a good example for waves. And these phenomena exhibit wave-like characteristics just like we saw in our oscillations unit. So these waves have a period, which is the amount of time that it takes for one wave to be completed, a frequency, which is the amount of waves passing in a given amount of time, and an amplitude, which represents the size of the wave. But also the wave travels outward from its source point, and if it's traveling, it must have motion, and if it's moving, we can say something about how fast it's moving. The wave velocity, VW, is used to describe the speed of a wave. And a wave also has a wave length, which describes how long the wave is, not its size, not the size of the disturbance, that would be the amplitude, but the length between successive points in a wave would be called the wavelength, and it's measured in meters. If we know the wavelength of a wave and its frequency, we can determine the wave speed simply by multiplying the wavelength and the frequency together. The wave speed strictly depends on the medium through which the wave is traveling. So for water, the density of the water and the pressure of the water will affect the wave speed in that water. The amplitude does not affect the wave speed. And for a particular medium, like for example, a string under tension, we can get waves to exist in this string under tension by using a frequency generator or a string vibrator. And we can find that the wave speed in a string under tension is dependent on the amount of tension being exerted on that string, as well as its linear mass density. This is a lot like density, which talks about mass per unit volume, but the linear mass density talks about mass per unit length. So it will have units of kilograms per meter. Since our string is a one-dimensional object, we really only care about how much mass is contained along that one dimension. There really isn't any width or height to this. It just has a length. So that's why we use a one-dimensional linear mass density. It's important to note that when waves travel, they do not actually move anything. If you imagine yourself in the wave pool at a water park, or sitting on a tube out in the ocean as waves are crashing into shore, you will notice that you don't actually move in your tube. You just go up and down with the waves. And that's because waves don't actually move any objects or any matter, but they do transmit energy. Because they have an amplitude, we know that a wave has energy. The energy is directly related to the amplitude of a wave, so the larger the amplitude, the more energy that wave will transmit. And remember that the amplitude goes down as a wave oscillates and propagates due to damping. So overall, the amplitude is going to go down for a wave as it travels, as well as its energy. We can see an example of a small amplitude, medium amplitude, and large amplitude in the string under tension, and here we have different amounts of energy that are being transmitted by these waves. There are also different directions that disturbances can exist in for some medium. So we have two major types of waves called transverse waves, where the disturbance direction is perpendicular to the actual direction that the wave is moving, versus a longitudinal wave, which has an amplitude in the same direction parallel to the direction of the wave speed or the wave velocity. So if your wave is traveling to the right, but the disturbance goes up and down, you have a transverse wave or a shear wave. But if the wave is traveling to the right and your amplitude is also a horizontal displacement, then you have a longitudinal wave or a compression wave. Here's an example of longitudinal waves and transverse waves in a slinky. In the slinky, you can see we have a compression in the spring that is being pushed to the right. And in the wave on a string, you can see that the amplitude is up and down while the wave also travels to the right. In the oscillation unit, we saw oscillation history graphs, which show you the position of an object as it oscillates with respect to time. We can also talk about a snapshot graph, which is what a wave would look like at one specific time. And that would display the horizontal and vertical positions of the wave throughout space for one specific time instance. That's why we call it a snapshot graph. And you will need to be able to use these snapshot and history graphs to figure out things like the period, the wavelength, and the amplitude of a wave. So here's an example of a snapshot graph versus a history graph. You can see in the snapshot graph that we have the Y position plotted versus the X position, and in the history graph you can see that we have the position of the wave or its displacement versus time. So that'll cover everything for Unit 11A. I'll see you in the next one.